Okay, so I'm gonna be recording example 4 using my phone instead of using my laptop and a stylus, just because I feel like it's easier for me to talk and write it out at the same time without having to worry about is my handwriting like legible, or is it just super messy and it's hard to follow along. And so in this example right here, this is slide 29. So we're going to be using the central limit theorem to help us find probabilities. The example tells us that 78% of laboratory mice can make it through a maze. If 600 randomly selected laboratory mice attempt the maze, what is the probability that more than 80% will make it through? So what I have outlined here is what I recommend students to follow because it's logical and it will lead you to the correct answer if you understand what's happening in each step. Of course, if you have a different preferred method, you can do that as well, but this will be an additional resource for you to look to. So the first thing, my step 0, would be to identify N and P, the sample proportion, and the sample size. If the sample proportion P is not given, go ahead and calculate P hat. So in this example right here, again, N is the sample proportion, N is the sample size. Do we know how many mice were randomly selected for the study? So here we're told that 600 of them were randomly selected, which makes our sample size 600. P is the population proportion. Do we know what the proportion of do we know the proportion of laboratory mice who can make it through a maze? In this case right here, we're told that 78% of them make it through a maze. And so our P in this case is 0.78. So now that I've done step 0, I'm going to move on to step 1. The reason why I recommend step 0 is if you have N and P defined in the beginning already, it's going to help make it easier when you reach steps 1 through 3. So step 1 again is checking the central limit theorem assumptions. We did an example on that in the last video. Here we're going to do the same thing for this new example. So the first thing to check is the sample random and independent? These two should have been combined together, but I'm going to go ahead and just write something and then throw an arrow down. So again, we're assuming that all of our samples are done with a simple random sampling. And because a simple random sampling is without replacement and also equally likely, that rules out the non-randomness. And so in this case, since the sample is assumed to be a simple random sampling, then our sample must be random and independent. So this is the nice thing about assuming that we have a simple random sampling, because we automatically get that it's random and independent. Now, the second assumption to check is the sample large enough? And so that's checking to see if n times p is greater than or equal to 10, and if n times 1 minus p is greater than or equal to 10. So again, remember that if you don't know p hat, or if you don't know p, you would substitute p with p hat. But thankfully in this case, p is given to us, so we're going to keep it the way it is. So on the left side, we're checking to see if 600 times 0.78 is greater than or equal to 10. And then on the right side, we're checking to see if 600 times 1 minus 0.78 is greater than or equal to 10. So if you solve that out, the left side we get 468, which is indeed greater than 10. And then on the right side, we get 132, which is greater than or equal to 10. So in this case, both sides are met. So our second condition, or our second assumption, is satisfied. our last assumption is checking to see if the population is large enough. So in other words, we're checking to see if n times, or if n, the population size, is greater than or equal to the sample size by 10 times. So we're checking to see if the population size is at least 10 times greater than 600 in this case. So 600 comes from the number of laboratory mice that were sampled. The population would then consist of all laboratory mice. So in this case, are all laboratory mice greater than or equal to 6,000? Yes, and so this is also checked. So as we have seen, all of our 3 requirements are checked. The sample is random and independent because of SRS. Sample is large enough as shown by our 2 sites. The population is large enough because all laboratory mice is greater than or equal to 6,000. And so since these 3 conditions are met, we can go ahead and make a conclusion about the distribution, or about the sampling distribution. So we know that the sampling distribution, sorry, there's so much typos. This is actually a sheet that I created last semester, and conveniently I have it with me. So we can make a conclusion about the sampling distribution. So we know that the sampling distribution will be approximately normal, and then the mean would be equal to p. P in this case is 0.78. And then the standard deviation is going to be equal to the standard error, which in this case we can calculate. So remember that the standard error has this formula right here. So that's going to be equal to 0.78 times the quantity 1 minus 0.78 all over 600. And then don't forget to take the square root, which is going to give us a standard error of 0.0169. So our conclusion is that the sampling distribution is approximately normal with a mean of 0.78 and a standard error or a standard deviation of 0.0169. So moving on to step 3. So step 3 is actually where we start to actually apply what we've done in steps 1 and 2 and find probabilities. So step 3. So since we did conclude that the sampling distribution is approximately normal, then we know from chapter 6 that we can find probabilities for a normal distribution. And so everything that we do in step 3 is everything that you have learned in chapter 6. Except that now we're not going to do it on the mean anymore. We're actually doing it on the proportion. But everything is the same, not much has changed. Specifically in this example, we want to find the probability that more than 80% of the randomly selected mice will make it through the maze. Because if we look at the question statement again, the question is asking specifically, what is the probability that more than 80% will make it through? Okay, so first thing to do in step 3 is again, sketching the curve, labeling it, and shading the area of interest. So here I'm drawing my symmetric and unimodal curve because we're assuming that it's normally distributed. The mean in this case is 0.78. Standard deviation, we calculated it as the standard error, which is 0.0169. So we know that one standard deviation above will change by 0.0169. So you can go ahead and pause the video and figure that out, or you can just go ahead and jot what I'm putting down now. So I've already calculated these beforehand. And then right below this, I'm gonna go ahead and just add my standard unit scale, my z-score scale. Okay, so I've drawn my curve, I labeled it. Now I'm looking for, or I'm gonna be shading the area of interest. So again, here we're looking for the probability that more than 80% of the randomly selected mice will make it through the maze. So in my curve right here, I'm gonna be looking for 0.8. 0.8 is going to be right around here somewhere. And then since I'm looking for the probability that more than 80% of them will make it through, I'm gonna be shading to the right, or in this case, this is the upper tail. So that's the area I'm interested in. So step 2 is making that transformation. So currently right now we have a normal model. We have to transform it into a standard normal model in order to find the probability. And so to do so, I just want to mention that in chapter 6, what we had was z is equal to x minus mu all over sigma. But since we're dealing with the proportion instead, we're going to have to modify this just slightly. So here, the standard deviation is the standard error in this case. And so the denominator becomes SE. The mean was mu in chapter 6, but the mean in this chapter is the population proportion. X is our data value, and similarly, our X, or our quote X, is going to be the proportion we're looking for, or the probability we're looking for, which I'm going to call P star. So again, P star is a proportion value stated in the problem that we're looking for, similar to the X value. P is the population proportion, similar to the population mean. Standard error is the standard deviation, similar to sigma in chapter 6. And so using this, we can go ahead and calculate what our z-score would be. So P star in this case is 0.8. That's the probability or the value we're given above here. Our population proportion is 0.78. Our standard error was calculated to be 0.0169. And if you solve that out, you're going to get a z-score of 1.18. Okay, so we have a z-score of 1.18, and then with our fancy z-score table or standard normal table, we're gonna look for 1.1, match it up with 8, which is going to give us an area of 0.0 or 0.881. So our z-score is 1.18. When z is 1.18, area is 0.881. Now, is this our final answer? So if we look at our curve again, we're shading to the right. We have an upper tail problem right here. So we know that this is not our final answer. So no, because this is an upper tail problem. And so whenever we have an upper tail, we know that we have to take the complement because the table only gives us the area to the left, not to the right. So 1 minus area is equal to 1 minus 0.881, which is going to be 0.119. So now that's our final answer. And so to wrap up this whole problem, we're just going to state a conclusion that makes sense for our problem. And so here we can say that to answer the question, there is an 11.9% probability that more than 80% of the laboratory mice will make it through the maze. Yeah, so our conclusion is just that there is an 11.9% probability that more than 80% of the laboratory mice will make it through the maze. So I'm going to go ahead and recap what we've done so far. So again, here we're given that 78% of laboratory mice can go or can make it through a maze. 600 of them were randomly selected to attempt the maze. We want to know what the probability would be that more than 80% will make it through. We first start off by identifying N and P. If P is not given, we calculate P hat. Step 1 would be checking the central limit theorem assumptions. If the assumptions are not met, there's no point in doing any of this because this is only true if the central limit theorem is met. So the first thing to check is to see if the sample is random and independent. Most of the cases, this is going to be true because we assume that the rest of our problems are done with a simple random sampling. Is the sample large enough? Again, you're checking both sides of them, not just one. If P is not given to you, make sure you're using P hat, and P hat can be calculated. Finally, checking to see if the population is large enough. Again, we're checking to see if the population size is 10 times bigger than the sample size. And here I want to elaborate that the population size doesn't always have to be a concrete number. It can be something as abstract as just all things or all objects, all people. If each of these requirements are met, we can go ahead and make a conclusion about the sampling distribution. So in this case, P was given to us. The standard error can be calculated. So the sampling distribution is going to be normally distributed if the central limit theorem is met with these two values. This is going to be super crucial when we move on to step 3 because this is what we need in order to draw our curve, label it, shade it, and find the probability. Step 3 is everything that you've learned in chapter 6. Chapter 6 has prepped us for this moment right now. And so here, we're just doing everything that we've learned, sketching a curve, labeling it, shading the area of interest, making a transformation from the normal model to a standard normal, except our formula is going to be changed a little bit just to meet what we're actually dealing with, because here we're not dealing with a sample and population mean, we're dealing with a proportion. And so P star again is similar to the X value. This is going to be the proportion value that you're looking at. P is the population proportion, similar to the population mean, mu. Standard error is going to be similar to the sigma that we used in chapter 6. So make sure you have this formula jotted down somewhere. And then after you find your z-score, finding area like you do. Again, if it's an upper tail problem, make sure you take the complement. If it's a lower tail problem, you don't need to do anything else to it. For this class, I don't think I'll be doing any in-between probabilities. But if that was the case, remember you have to take the difference between the two areas. And then finally, making sure that you have a conclusion that makes sense for the problem.